One thing that we should think about doing is distinguishing the properties that a matrix has because it represents a linear transformation and the property that it has because of the basis that you've chosen for the domain and range space for that linear transformation. We've seen that if you have a linear transformation, what matrix represents it depends on the basis for the domain and range space. So in general, if you have a linear transformation from one subspace to itself, if it has some matrix A, if you change the basis for V, that will change what matrix represents this linear transformation. So we should try to figure out, well, any property that this matrix has that depends on the basis that you chose isn't really a property of the linear transformation. But on the other hand, if there's some property of the linear transformation, that should be reflected in every matrix that might represent that linear transformation, no matter what basis that matrix is with respect to. So what we should do is, to try to figure out properties of linear transformations, is try to figure out what things do and do not change when you change the basis that a matrix is with respect to. So to be able to answer that question, the first thing that we need to do is just figure out, well, if you change a basis, how does the matrix for a linear transformation change? So if we have a linear transformation from Rn to Rn, it's relative to the standard basis, it has some matrix, right? That's usually what we think of as the matrix for a linear transformation from Rn to Rn. It's the matrix relative to the standard basis. But what if we change the basis? So let's change the basis to maybe some new basis made up of, say, some vectors v. So there have to be n of them if A is n by n, and they have to be linearly independent to be a basis. So in this situation, right, we have this coordinate map that sends each vector in the basis to the standard basis vector, right? This picture is going to get a little confusing because we have so many copies of Rn lying around, but that's life. The inverse of this coordinate map, that's the map that just sends EI to VI. And the matrix for this inverse coordinate map, this is just the matrix whose columns are the V's, right? So this matrix is going to show up again and again, so let's give this a name. I'm going to call this P, okay? Yes. And over on the range space side, remember, we're thinking of these two copies of Rn as being literally the same because we're thinking about a linear transformation that goes from one subspace to itself. So if these two copies of Rn are literally the same thing, then it makes sense to use the same basis over on this side. And so the coordinate map over here sends the basis Vi to the standard basis EI. And what will the matrix for this linear transformation be? Well, right, we have the matrix P is the matrix that sends the EI to the VI. We're going the other way, so this is just going to be P inverse. Okay, now the matrix relative to our new basis is the matrix that sort of fills in the bottom of this square. So we need to figure out what this matrix is. But we have a matrix for each step along the other three sides of the square. So if we had some vector over here in our bottom left copy of Rn, where would it get sent over in our bottom right copy of Rn? Well, we're starting with V. First we need to do this inverse transformation on the left-hand side of the square, but the matrix for that is P. And then we need to take the step across the top of the square, but the matrix for that is A. And then we need to do the step on the right-hand side of the square, but the matrix for that is P inverse. So the matrix, so we started with a matrix A, we changed to the basis for Rn, and what we got was a matrix P inverse AP. So that means this matrix, P inverse AP, this is the matrix for this linear transformation relative to our new basis B. Right? So what that means is these two these two matrices, even though they're different, they share sort of a, I don't know, sort of a soul, I guess, because they're representing the same linear transformation, just in different bases. So if any two matrices are related in this way, we'll give that relationship a name. Okay, so when two matrices are related in this way, so that one of them is just, right, if there's some invertible matrix P, so that the first one A is P inverse times the second one B times P, then we say that these two we say that A and B are similar. Okay, and the notation for that is just this squiggly line. So A is similar to B. And remember, what being similar means is that both of these matrices could represent the same linear transformation, but just relative to different bases. Let's look at some properties of this relationship, this similarity relationship. So one thing that's fairly clear is that any matrix is similar to itself, right? Because what we're looking for is, can we find a matrix P so that A is equal to P inverse A, P inverse? And yes, the identity matrix will work. So A is always similar. Any matrix is similar to itself. This property is called being reflexive. So this is the reflexivity of the similarity relationship. Also, if A is similar to B, then B is similar to A. That's pretty clear, because if A is similar to B, then that means we can write A as P inverse times B times P for some matrix P. But then we can rearrange this equation. We can multiply on the left by P and on the right by P inverse, and that gives us P A P inverse is equal to B. But then we can just sort of rename our matrix. Let's instead of calling P P, instead of calling P inverse, let's call it M. And then M inverse is P inverse inverse, but that's P. And then if we rewrite this thing using our new names M, we get M inverse A M equals B. And this shows that B is similar to A. So really, this relationship similarity, it doesn't matter which order you write it in. This property for a relationship is called symmetry, when it doesn't matter which order you write it in. And then the last property is transitivity. If A is similar to B and B is similar to C, then A is similar to C. This is also pretty straightforward. If A is P inverse B times P, and B is similar to C, so that means we can write B equals some matrix, say M inverse times C times M. Well, if we just plug one of these into the other, we get A equals P inverse M inverse C times M times P. But then we can rewrite this as M times P inverse times C times M times P. And then this shows us that A is similar to C. So this property of a relationship is called transitivity. And if you have a relationship that is reflexive, symmetric, and transitive, it's called an equivalence relation, or equivalence relationship. And there are lots of important equivalence relationships out in the math world. So you'll run into this sort of relationship again, I'm sure. The important thing about equivalence relationships is all equivalence relationships do this, but the important thing about this equivalence relationship is that it breaks up all of the n by n matrices into so-called equivalence classes that is collections of matrices that are all similar to each other. And it turns out that's sort of an important thing, which we'll get to later. There are some other important facts about similar matrices. I'm not going to prove all of these because it would take us a little too far afield, but some of them are pretty straightforward to show. So one is that if you have a similar matrix, if you have similar matrices, their determinants have to be the same. That's pretty straightforward because, the determinant of A, if it's similar to B, then we can write A is P inverse times B times P. But then we can break this determinant up So determinant of P inverse times determinant of B times determinant of P. But then the determinant of P inverse and the determinant of P, those are reciprocals, so those are going to cancel, and we just get the determinant of B. So that one's pretty straightforward. Rank of A equals rank of B. This has to be the case because because of this similarity relationship, A is equal to P inverse times B times P. If you just think about the dimension of the row space or column space for A and B, and think about sort of what an invertible matrix will do to the rows or the column, or what it will do to the rows or the columns, you'll see that the ranks have to be the same. So that requires a little more proving, but I'll leave it at that for now. Something that's very not obvious, but I am not going to prove, is that the characteristic polynomials for similar matrices have to be the same. So that's kind of a surprise. So I don't think I've used this notation before, but little c sub a, that's just the characteristic polynomial for the matrix A. So characteristic polynomial for A has to be equal to the characteristic polynomial for B when A and B are similar. Another item that is a bit surprising is that similar matrices have to have the same eigenvalues. This is actually not that bad to show. So suppose we have an eigenvalue, lambda. So if we have an eigenvalue lambda for A, then that means A times V is lambda times V. Let's show that this is an eigenvalue for B. Well, remember that if A and B are similar, then that means that we can write B as P inverse A times P. Actually, I want to write this the other way. That means we can write A as P inverse times B times A times P, sorry. Okay. Well, we can just replace A in this equation with P inverse B times P. Okay. And on the right-hand side, that's lambda V. But then we can multiply both sides by P, and that gives us, on the left, multiplying by P, we'll have a P times P inverse, so that's the identity, so that goes away. We get B times P times V equals P times lambda times V. But now look, we have B times this vector, PV. And on the right-hand side, this is lambda times the vector PV. So PV is an eigenvalue for B with, sorry, an eigenvector for B with eigenvalue lambda. So we started with an eigenvalue for A, and we showed that we have to have that same eigenvalue has to be an eigenvalue for B. And of course, this argument works backwards, so any eigenvalue for B is also an eigenvalue for A. Notice that the eigenvector is actually different, right? The eigenvector we started with for A was V, and the eigenvector for the corresponding eigenvector for B is P times V. Okay, one last property of similar matrices is that they have the same trace. This I'm not going to prove, but just to tell you what the trace is, the trace of a matrix is, if you write it fancy, it's the sum from 1 to n of ai. This is just the sum of the diagonal entries. Okay, so turns out that similar matrices, if you add the diagonal entries for both for A and B, you get the same thing if they're similar. So a bit of a surprise. I'm not going to prove it, but turns out it's true.